I try to imagine a fellow smarter than myself, and then I try to think, what would he do?
Charge up your axons, ready your receptors, and shift your lobes into upper beta phase. You are listening to Smart Drug Smarts, the podcast dedicated to helping you optimize your brain with the latest breakthroughs in neuroscience, nootropics, and psychopharmacology.
Hello and welcome to Smart Drug Smarts. I am your host, Jesse Lawler, excited to bring you episode number 104, which also happens to be our 3-year birthday episode for this podcast. 2 days from now, I think, is our 3-year anniversary of the first publication of the original episode of this podcast. And oh, what a 3 years it has been. But we are talking this week with a scientist with a background of 3 decades, not just 3 years, working in neuroscience, Dr. Vincent Clark, currently at the University of New Mexico. We are going to be having a wide-ranging conversation about neuroimaging, transcranial direct current stimulation, transcranial magnetic stimulation, the use of dental orthotics to improve cognition. If you thought that what you're doing with your mouth and jaw has nothing to do with the operation of your brain, by the end of this episode you will be thinking differently. It's a pretty interesting conversation. We talk about the legality of drug design and some of the problems with the profit motive incentive system that we have in the US. It's a little bit of a longer episode, but I think well worth it. So sit back, grab a cognitive enhancer of your choice. If you hang around until the very end of the episode, I'm going to tell you something that science has recently figured out to shed some light on that old question of why people that are experiencing marijuana tend to also clean out the refrigerators and eat everything in sight, a phenomenon colloquially known as the munchies. That'll be in the ruthless listener retention gimmick. But as usual, let's kick things off with This Week in Neuroscience.
Smart Drug Smarts, This Week in Neuroscience.
So imagine that you're a mouse and you're approaching this big luscious piece of cheese and you really want to eat it, but you heard that several of your mouse friends also saw big luscious pieces of cheeses on something that might have looked similar. You're not exactly sure, but they met grizzly ends, and you have yourself a mouse-like dilemma. You've got perceptual information coming in that's attractive to you, but you also have fear. You also have this nagging emotion of anxiety that's creeping up and making you have a conflicted decision. In psychology, this conflict is known as approach avoidance. These types of decisions are among the most interesting decisions we make when it's not something purely perceptual, like saying, which of these two lines is longer? Do I want to have a cheese sandwich or a bologna sandwich for lunch? And I've got plenty of both. But something where you've got incoming perceptual data from the real world and you've also got some strong emotions built around it. And those two types of input might sometimes be in conflict with one another. How are these decisions made? Well, according to new studies by some MIT neuroscientists, there's something called striasomes, which are apparently intimately involved with these sorts of complex decisions. These cell clusters are distributed through the striatum, which is a large brain region beneath the cerebral cortex that's known to be involved in coordinating our movements to our motivations. But striasomes are so small and they're so deep inside the brain that scientists have had a hard time imaging them with fMRI studies. But there was reason to believe that this region might be implicated in making some of these emotional types of decisions based on monkey studies where this region is not buried so deep under other brain tissue, and this area seems to be active in approach avoidance conflicts. So to study this in mouse models, scientists looked at something called optogenetics, where they were able to stimulate different neurons with light sources to look at what regions of the brain seem to be active in these approach avoidance conflicts. They took some mice, they put them in a maze, and they gave them a tough choice. They had 2 paths, and one of them had strong chocolate, which the mice like, but also some bright light, which they don't like. So some strong positive and negative inputs in one direction, and then another tunnel had dim light, but some weak chocolate. So kind of high risk, high reward down one pathway, low risk, low reward down the other pathway. A classic approach avoidance decision. They also gave the maze-running mice a bunch of other tasks that involved some decision-making but didn't have the same emotional component to the decision-making processes. And they used optogenetics to intentionally trigger these cortical cells, these striasomes, during each of these 5 decision-making processes. Lo and behold, it was only during these emotionally rich approach avoidance conflicts, like the one with the bright light and the strong chocolate, that optogenetically triggering the striasomes made any difference. So the striasomes appear to absorb sensory and emotional information coming to them from the cortex and integrate the 2 of these to produce a decision. Ultimately, the scientists suspect that this new research may lead to some treatments for anxiety and other mood and emotional disorders.
Just say no to scratch that. Say yes to the Smart Drug Smarts podcast. Join our mailing list at www.smartdrugsmarts.com.
Happy to report that we picked up a couple of 5-star reviews on iTunes this week. PGP Mail says, excellent podcast. It's helped spark an interest in brain health, supplements, and nootropics. It's literally food for thought. And Josh Trent says, my go-to expert for nootropics and brain health. Beyond just a unique voice and an energetic personality, Smart Drug Smarts delivers the education and tools that can truly make an impact in the lives of listeners. Thank you for what you do. And thank you guys for what you do. Positive word of mouth and digital word of mouth as well. If you feel like leaving a positive review for Smart Drug Smarts on iTunes and you're not quite sure how to do it, we have a super short, super easy instructional video at smartdrugsmarts.com/rate. Or if you already know, you can just go to iTunes. Also, over at smartdrugsmarts.com, we've got a newsletter sign-up page at smartdrugsmarts.com/newsletter if you want to find out what's going on. This week, actually, I got approached by a major television network that you have heard of. They're looking for people that are experimenting with nootropics between the ages of 18 and 29 for something that they're going to be shooting really soon. It's got to be within the continental United States, and it's got to be quite fast. So this episode will be hitting on Black Friday, right after Thanksgiving. If it's within a week after that and you're interested, just shoot me an email at jesse@smartdrugsmarts.com and I will connect you with the right people. Don't do it if you're camera shy, but if you don't mind television cameras and you do have an exciting story about why it is that you felt motivated to improve your cognition, you might be who they're looking for. And in honor of it being Black Friday, that shopping holiday that all of us in America love to hate, we've got a very lovable 15% off across-the-board sale going on over at axonlabs.io, where we've got our couple of stacks, Nexus and Mitogen. Nexus, our cognitive stack built around aniracetam, CDP choline, phosphatidylserine, and pycnogenol, and Mitogen, our mitochondrial booster stack, which is an absolutely everyday thing for me, both for physical and mental performance. I like one with my cup of coffee in the morning as I wake up. I like two the hour before my workout to make sure that I'm fully energized. And it's got long-term benefits like the growth of additional mitochondria, which come in especially handy in energy-hungry cells like your brain cells. So all of this and more over at axonlabs.io. It is the Christmas shopping season. You've probably got some folks on your list. Those folks probably have brains, and wouldn't they be thrilled to know that you're thinking of them, their brains, and their long-term cognitive health by getting them some jars of brain and body healthy supplements in their Christmas stockings, or whatever gift distributing apparatus your holiday of choice entails.
Smart Drug Smarts.
So a good 10 episodes ago, we spoke with Dr. James Giordano. We talked about a bunch of different electrical stimulation techniques for the brain, including both things crossing the skull and also deep brain stimulation that actually goes inside the skull. A really interesting conversation, worth checking out if you missed it. But at the end of that, I asked him, who else do you know that's doing amazing work in this field? And one of the first names that came to mind for him, who he was kind enough to introduce me to, is our guest today, Dr. Vincent Clark from the University of New Mexico. He is a professor and the director of the Psychology Clinical Neuroscience Center, and the founding chair of the Brain Stimulation and Imaging Meeting. Brain imaging, advancing the science of getting the best possible look of what's going on within the brain, has been one of the main foci in his career, and something that you will hear he is very, very passionate about, particularly how proper imaging can be sort of a multiplier for different treatment techniques, so we can see what sort of interventions are effective, see why they're effective, and hopefully find ways to even multiply that effectiveness. This talk is all over the place. We touch on a lot of different topics, and it's really just great to hear somebody that's so enthusiastic and clearly passionate about the field that they're working in. So with no further ado, Dr. Vincent P. Clark.
So I started out as an undergraduate in a neuroimaging research lab in 1984. So here we are a lot later. And at the time, I had high expectations. I thought, well, we have all these new devices. We'll start to look at how the brain works. We'll understand it. We'll be able to cure things like addiction, alcoholism. We'll be able to cure things like schizophrenia very soon once we understand what's wrong and what's going on in the brain. And here we are over 30 years later, and people are still dying of alcoholism. People still plagued by schizophrenia. We have medications to treat some of these illnesses, but a lot of them don't work very well, and there's still much room for improvement. So at some point, I started to get a bit discouraged, since we're learning a lot about all these disorders, so learning a lot about the healthy brain, about the sick brain, but it's not really turning into practice. Why is that? And looking at medicine, a lot of medicine is focused on pharmacology, so giving people drugs. But in fact, most of what we know about the brain, although there's a lot about neurochemistry that we've learned, there's a lot more about basic function and about networks and about how these networks interplay with each other to produce behavior. But using pharmacology to influence that turns out not to be very effective or efficient to alter brain networks and brain function. It turns out that there's other methods to target those networks, and those are based on electromagnetics rather than being based on chemistry. So in 2007, I proposed a project where we used a combination of neuroimaging and electrical brain stimulation, TDCS, to try and enhance learning in a difficult visual perceptual task. And long story short, it worked remarkably well. If we use the neuroimaging data to target specific brain areas that were involved in the task and that changed their activity, changed their organization as people learned how to do the task, and sort of influence the brain to look more like an expert brain more quickly, people actually learned the task more quickly. They became experts more quickly.
What was the nature of the task in question?
We had these complex pictures, and we hid objects in the pictures that people had to learn to identify. And this was funded by the DoD, so the pictures were from the Middle East, and the objects were things like IEDs and snipers and so on.
Sort of the military version of Where's Waldo?
Yeah, exactly. And when people looked at the images at first, they had no idea what the hidden objects looked like and where they were. And they performed basically at chance at 50%. And then with training, they would slowly improve their performance, and you can track that over time. So over an hour's training, people typically gained around 15, 16% in their ability to recognize these hidden objects. Then if we compared people receiving TDCS and people receiving fake or sham TDCS, people receiving real TDCS over certain brain areas doubled their learning rate. So at the end of an hour training, they were twice as good as people who didn't receive TDCS or received sham TDCS.
Basically, if their baseline was like 50-50 at the start, they would go up to about 30% improvement rather than 15% improvement over that?
Depending on details of the task and so on, yeah.
Wow, that's a huge difference.
And so we first got these results, and the areas that seemed to respond the best weren't visual areas, which was my initial prediction. It was actually frontal cortex and parietal cortex. All of your brain gets involved to some degree in visual perception. It's just a matter of how much. And frontal parietal cortex is known to be involved in visual attention, but also in a lot of other things. So it wasn't really what we expected, but in fact, that's what the neuroimaging told us. And when we targeted there, we got the biggest effects. When we put the electrodes over visual cortex, we actually get almost no effect.
So it seems to be more of a cognitive task than a perceptual task in sort of the raw sensory data.
Yeah, and I think in general what's going on is these attentional networks that we've developed outside of visual cortex are designed in a way that helps us not to be fooled by objects that are trying to camouflage themselves. During evolution, our ancestors, in Africa and so on, they went out hunting animals that were camouflaged and were being hunted themselves by other animals like lions and tigers and so on that had their own camouflage. Our ancestors had to learn to recognize objects that were trying to hide from us, that were camouflaged. That was probably, I think, really important for the development of our visual attentional system. And it hasn't been studied hardly at all for some reason. But we were one of the first to really look at this closely. And by identifying those networks and stimulating them, we could actually enhance people's ability to detect camouflaged objects.
That's such a strong finding. I mean, such a big result. What's gone on since then, in the couple of years since that first study?
Well, following up on our work, there's a group in the Air Force Research Labs that has tried this using other forms of visual stimuli that are difficult to interpret. And they've also seen benefits of stimulation. In my lab, what we got really interested in is what else can we use TDCS for? What else might it be good for? So we did a lot of work, first of all, following up on the mechanisms of TDCS. And there's two findings that I think are important. One of them is that TDCS that enhances your ability to detect hidden objects also enhances certain forms of attention. And I think part of what's going on is that the TDCS is enhancing your ability to attend to certain kinds of information in your environment. And that increased focus helps you to learn to do the task better. Another finding that we have is that the TDCS protocol that helps you identify hidden objects also increases glutamate and glutamine. What that could be doing is enhancing plasticity in your brain. And plasticity is this general concept that your brain has to physically change when you learn something. What seems to be happening is that by increasing glutamate and glutamine, it adds a little bit of extra activity in the parts of the brain you're using to perform the task. That might help you to encode new information and make it more likely that you'll recall a previous event later on when you need it, which is what learning is, basically.
So what's the mechanism that the TDCS from the outside is encouraging biochemical result on the inside?
So we used magnetic resonance imaging, and there's a way to do that that you can look at specific neurochemicals. So we set that up, we scanned our subjects, got an estimate of the concentration of different neurochemicals in the brain, both underneath where we put the electrode and in the opposite hemisphere. And then we took them out of the MRI, performed TDCS for half an hour, put them back in the MRI, and did the spectroscopy again to look at the change. And we saw underneath the electrode, there's an increase in glutamate and glutamine, but not in the opposite hemisphere. Also, there is an increase in something called N-acetyl aspartate that seems to correlate with neural activity or brain activity in general. So areas that are more active have a higher level of N-acetyl aspartate. It looks like the area of the brain underneath the electrode was more active and was producing more glutamate and glutamine in response to the TDCS. So that's one set of studies. We've been trying to understand mechanisms. We're also recording EEG while people receive TDCS. One of my students did his dissertation work that way, and he found a lot of really extraordinarily large changes in brain activity. And I have another student, Michael Hunter, that's following up in his dissertation. He's also seeing a lot of really interesting changes in brain activity and brain waves in response to TDCS. And we're still trying to understand what that means in terms of changes in brain organization, but it seems like specific brain networks are enhanced by TDCS. And that enhancement both changes your behavior that we can record, your accuracy at doing a task or your ability to recognize something, and may be involved somehow in these changes in attention that we see.
How long in the protocol that you're using are people actually receiving the TDCS?
Typically for 30 minutes, and typically about 2 milliamps of current. And it's a pretty small level of current. About a third of the people that get it hardly feel it. And I think a lot of them think we're lying to them and we're not actually applying current. They think they're placebos. And then about 1% of the people we give it to feel it so strongly that they want us to stop. And the other 69% of people fall somewhere in between. So it's relatively rare that people find it uncomfortable. It's more common that people don't even feel it than find it uncomfortable by 30 times.
When you were trying to isolate the right areas to stimulate to get the best result, did you find a corollary where there are areas that you might stimulate where you could actually negatively influence somebody's perception of these visual cues?
We haven't been able to find a region that reduces it. We have found areas that show no effect, but we haven't yet found areas that show a reduced effect. There are other studies where they have shown reduced behavior, reduced performance with TDCS. We just haven't found it yet. If you look in the literature, we have a review article that came out last year. And we found that on the average, the reports in the literature show enhancement more than deficits, but in fact, the degree of deficits are close to on par with the degree of enhancement. Most of us are just interested in enhancement. What can we do to improve? And people get the impression from that that's the only thing you can do. It's not really true. There's a lot of examples of reduced performance using TDCS as well.
Have you kept up to speed with the TDCS models that are on the consumer market for things like playing video games faster and more effectively and some of the do-it-yourself communities that are around? And have any thoughts on that?
A little bit. I mean, a few thoughts are, as an objective scientist, what they're doing is very unscientific. And that can be okay if it works, and maybe it does work. But the bigger problem, I think, is that we still aren't entirely sure what the effects of long-term TDCS usage might be. And a lot of the safety studies are done after one application or maybe a few applications over a week or something like that. If you get someone using it an hour a day for a month or a year, we have no idea what that's going to do to somebody's brain. And a lot of those people doing it don't realize that it hasn't been tested that way. They think it has been tested because they can buy it and they trust that regulatory agencies are doing their job. It turns out that they're not. And I think it's really important for people to understand that if you're going to do this daily for a long time, you become an experiment. If you show up in the emergency room with some horrible neurological problem, make sure you tell them that you were doing this for a long time and that the word gets out there that there might be a problem for long-term use. It's not a loophole exactly, but it's the case that something that may have medical effects, that may have clinical effects on a user, if it's not sold for clinical purposes, doesn't have to be tested for those effects. And it may be completely safe. It's just we don't have the data one way or the other to say that it is safe or not safe for long-term use.
When your brain's just normally doing its thing, you're awake, it's humming along, what amount of electrical activity is going on normally versus the amount that you would be applying from the outside with something like TDCS?
That's an interesting thing. It's actually the level that we use for TDCS seems pretty small compared to the level of activity at the membrane surface of a neuron. And once it makes its way through the skull actually is very resistive. So a lot of the current doesn't get into the brain. And in fact, there's some evidence that in some cases, none of the current actually gets into the brain, but what you're doing is generating an electrical field, and the field gets through the skull and into the brain. And then somehow it interacts with neurons in a way that alters their level of activity, either up or down, depending on a lot of factors that are hard to control. Based on what I thought I knew about the brain up to 8 years ago, I would have predicted that there'd be absolutely no effect to what we're doing. It's such a small current. It shouldn't have much of any effect, but somehow it does. And it's still a question to me exactly how. We see effects. We see increased glutamate and glutamine. We see changes in how people behave. I know it has an effect. But what it must be doing, or what we think it's doing, is biasing the neurons just a little bit to increase the level of activity just a few percent or decrease just a few percent. And the system must be so sensitive that tiny alteration in activity must be enough to alter the activity of the whole network, which in turn alters your behavior and makes you better at identifying hidden objects or pay more attention to something. We still need a bit more data to understand this. And people are acquiring that data. They're doing work in animals, ex vivo work, so taking pieces of brain tissue out of an animal and applying electric fields. That kind of work has been done for over half a century now. And even back in the 50s, they knew that applying electrical fields to brain tissue altered its activity. And they got really intrigued about all of it, but then somehow lost interest and went on to more work in pharmacology than electromagnetics. And it just kind of dropped. But on the sidelines, a lot of people for a long time have actually been trying different forms of electromagnetic stimulation to treat different illnesses. As of now, there's actually dozens of different devices on the market that are approved at some level for treating different forms of illness. TENS units are one to reduce pain. So electrodes that you apply to your skin, it applies a varying current, and that helps reduce the pain signal that gets to your brain.
Why do you think that this has gotten less attention than pharmaceutical approaches?
Well, in the US, we have a for-profit medical system. A treatment that earns more money for the company that provides it or the people that provide it is going to be used more because it's more expensive. And it's sort of counterintuitive. You would think that if it was more expensive, people would use it less in favor of something that's cheaper. But in fact, that means that the doctors and the hospitals and even the insurance companies, probably the insurance companies, make less money if they use cheaper alternatives. Also, if you try and develop a new treatment to go to market, there's a lot of cost involved with that development. The FDA requires a lot of testing. It's very expensive. You need a lot of highly skilled people to work for months or years. You need to recruit patients. You need to monitor the patients. You need to make sure that it's safe. You need to make sure that it's effective and so on. There's a lot of work that needs to be done. The cost adds up to the millions or billions. For pharmaceutical companies, spend an average of $12 billion for every drug that comes to market. That includes a lot of failed drugs. So the cost for a successful drug is less, but you have to include the cost of all those failed drugs. If you have a cheap device like TDCS, it's a 9-volt battery, an electrical circuit, you can buy a system for a few $100s, and people can make them for much less. Although I wouldn't advise that because you want to be sure you're not getting too much current and so on. So an approved system that's been tested is a few $100s. That doesn't make the money back of all the testing that would require to make sure that it's safe for long-term use, to be sure that it's effective in a double-blind clinical trial. So that doesn't get done. So we're stuck. Our system actually forces us to develop expensive alternatives. And those are what are made available to doctors that doctors give to their patients. They can only use what they're given. They're stuck, and it's not fair. I think what needs to happen is a sea change where the government gets involved
It's almost something you'd like to see, like a crowdfunding platform around this, where if somebody can convince enough members of the public that, hey, this is something that really should be tested, but we're going to need to do a bake sale for $5 billion or whatever it is, then at least people have the opportunity to kind of vote with their wallets and test some of these things out.
Yeah, exactly. That's one way. But I think, too, that the National Institutes of Health, which is one of the largest funding agencies in the world developing new medical treatments, needs to understand that it has a responsibility to bring down the cost of healthcare. The cost of medicine shut down our government 2 years ago. People forget that stuff really quick, but it was the cost of medicine that led to what's commonly called Obamacare. It caused huge political problems still for Obama and for the Clinton White House before that. It's a huge national problem, and no one's working that hard to reduce the cost. People are actually quite happy that the massive increase year by year in the cost of healthcare has started to level off somewhat. Now it's at $2.7 trillion a year, and half of that is paid by taxes. So even if you're not paying it to your insurance company, you're paying it through taxes, and your taxes are used to fund healthcare for people that can't afford it, for the VA system, and so on. So it's a huge problem for us. And our $18 trillion national debt, a significant portion of that is accounted for by the cost of healthcare. So I think that cheaper, potentially safer alternatives like TDCS could provide an alternative answer to the cost of healthcare besides Obamacare.
Here you were talking about TDCS as a medical treatment, I guess, to solve problems for people that have some particular illness or situation that they're trying to deal with rather than just performance optimization. Can you tell us some of the applications there?
We've worked with a few. We found an interesting thing. When we gave people TDCS to enhance their learning, we asked them, how do you feel? Do you feel any different? And strangely, most people said no, they don't feel any different at all, even though they're able to learn our task twice as fast. I thought that was kind of odd, but as we asked around, eventually we found people that had a history of doing meditation, and people that were active expert meditators said that TDCS, the way that we were administering it, felt a lot like meditation, and in fact felt like the second or third day of a 5-day retreat almost immediately for them. So that's something interesting that we're following up with in different ways. Meditation is another example of a relatively safe, inexpensive thing that you can do that has a lot of health benefits. It reduces stress, it reduces blood pressure, reduces anxiety, reduces depression in a lot of people that are depressed. The problem with meditation is it's very hard to learn for some people, and they give up right away. They don't feel it. They're annoyed by it. It's hard for them to do. What we're trying to do now is use TDCS in combination with meditation to help people learn how to meditate faster and better and get them over the hump of learning how to meditate.
How does that learning process work?
So Katie Wickowitz in my department at University of New Mexico Department of Psychology and I have been working together on this. And Katie's an expert on mindfulness, meditation, and uses it to treat addiction. So we have some funding to be able to use a combination of TDCS and training mindfulness to help people reduce their smoking. So we sit people down in a room, have them hooked up with electrodes for TDCS, and then go through mindfulness training. And to do that, you have people sit with their eyes closed and they listen to someone talking them through going into a mindful state. And what we found in a pilot study was a good reduction in smoking on the part of people doing that, and also a reduction in drinking. So we put a proposal into the National Institute on Alcoholism, and we got a good score. So hopefully we'll get funded and be able to look at that. Another way that TDCS is shown to be helpful is in schizophrenics who hear voices. And in schizophrenia, if you ask a schizophrenic, what's the worst part? A lot of them will say it's the voices I hear in my head, which very often are negative, and telling them they're horrible people, that they're going to hell, that they should kill somebody else, whatever. And if you think about it, having someone yell at you like that 24 hours a day, 7 days a week for years, what that would do to you as a person. And that's what they go through. It's horrible. So there was a group in Lyon, France, that found a TDCS protocol that reduced these voices on the average about 30%. But for some people in their study, it was much larger and the voices went away almost completely. And we're trying their protocol here now at University of New Mexico and the Mind Research Network. And what we're finding is that about a 30% reduction in the voices that people hear receiving this TDCS protocol. So we're replicating fairly well the results that the French group got. And the very first patient in that study had been hearing voices for about 20 years. And she said the first day of treatment, her head was quieter than it had been for 20 years. And it stayed that way more or less for 3 months after we ended treatment. So this is something we're really excited about because there's drugs that have effects on voices that reduce voices, but they don't work really well for most people. And for some people, they don't work at all. So this might be an alternative or an additional treatment that you could use so that people don't have to take the drugs and deal with the side effects as much.
We've talked a lot about TDCS. I know that you've done some work with transcranial magnetic stimulation also. Can you kind of compare, contrast your interest in those two?
Yeah, so I run a research center, the Psychology Clinical Neuroscience Center, and we have a TMS system there. There's a couple of interesting differences. One of them is that you can buy a TDCS device for a few $100s. TMS devices are a few $100,000. They're much more expensive. A TDCS device weighs less than a pound. A TMS device you can hardly pick up. So it's not portable. TDCS influences brain activity by biasing it just a little bit. So you get a slight increase or decrease in brain activity as a result of TDCS. TMS produces a large, very fast, very rapid shock to the brain in a sense, and not a real shock, but what it does is to induce action potentials in the brain. So that has a much larger effect. I happen to work with a fellow named Mark George at the National Institutes of Health who spearheaded the development of TMS to treat depression. Through his efforts and the efforts of other people, this method got FDA approval for doctors to bill to use TMS to treat depression a few years ago. And as far as I know, it's one of the first FDA-approved brain stimulation methods to treat clinical disorder. And that really started a watershed of looking at methods to use brain stimulation that will help clinical disorders. So in this case, it's a relatively expensive device. There's more resources to be able to develop it as a clinical tool and get approval. Now, one interesting thing is TMS uses a pulse of magnetic field to do what it does. TDCS uses a constant electric current. It turns out for both magnetic and electrical stimulation, you can modify the level of either magnetic field or electrical field over time in different ways to produce different effects. Besides direct current, there's also alternating current, and it can alternate within a sine wave function from very slow to very quick. And the same is true for magnetic fields. So you can have a static magnetic field. Some people are experimenting just with very strong static magnets and seeing effects on brain activity with static magnets, or pulse for TMS, or alternating magnetic fields. For both magnetic and electrical fields, you can also use random noise. It turns out that if you add up all the different ways for just electrical stimulation, it actually turns out to be in the quintillion range. And there haven't even been a quintillion seconds since the start of the universe. So there's multiple quintillion ways to apply electric current to the brain. That doesn't include magnetic stimulation. And in addition to electrical and magnetic stimulation, ultrasound can also influence brain activity. And even certain frequencies of light will interact with enzymes in the brain and alter brain activity. We have just started, this is just the tiny tip of the iceberg, or even the snowflake on top of the iceberg that we've started to look at. There's so much more. It's mind-boggling, really, to think of all the possibilities there. If TDCS applied one certain way doesn't work to treat a disorder, you have a quintillion minus one other option, not to mention these other forms of stimulation that you can do. And even just physical pressure. We have a whole other series of studies that use devices like orthotics that you can put in your mouth that were developed by dentists who realized that some of their patients that came in for dental problems that also had neurological problems, when they treated their dental problems, their neurological problems got better. And this was things like chronic pain, dystonia, where your muscles lock up and you can't move, tremor, and Tourette syndrome, where you have tics and vocalizations. All those things got better for some of their patients when they treated problems with their teeth and jaw. There's this really interesting connection between the nerves that innervate the mouth and jaw and the face and neurological problems that can develop. And neurologists that treat these illnesses aren't taught anything about that relationship. And honestly, it's because very little is known. But these dentists that have realized that they might have something there and have started to develop it have treated successfully a lot of patients with otherwise untreatable illnesses or that require really heavy medications with a lot of side effects that are unpleasant. And for some of them, just putting an orthotic in their mouth, a lot like what people wear after they have braces, it's not an extreme device at all, is enough to cure or at least cure the symptoms of their neurological disorder.
That raises a really interesting question, too, for people that don't necessarily have a neurological disorder. But if there still might be a way of modulating how your brain is working with a dental orthotic.
So actually, there's somebody that's developed and patented and markets an orthotic for football players. A lot of them wear that device in their mouth so they don't crack their teeth. If you alter it just a little bit and alter how it applies pressure to the mouth, these guys say that it increases your strength, increases your pain tolerance, and makes you a better football player. Some teams have actually adopted it and use it. Also, if you think in history, before anesthetics, before we understood how to reduce pain, when people had surgery or when women were having babies, they'd give them something to bite on. And our modern thought about that is, oh, well, maybe they'll crack their teeth. But why do you clench your jaw so much when you're in pain that you might crack your teeth? And why were they doing that? And it's true all over the world. I went to China and talked about this, and the Chinese did the same thing. Pretty much every culture had this history of people biting when they were in pain.
I remember reading about the berserkers of Viking warriors back hundreds of years ago. They would bite down on something hard like their shield before going into battle to kind of psych themselves up for it.
Yeah, I hadn't heard about that, but it's probably the same thing. Through evolution, it looks like we are set up with a very strong connection between our jaw and mouth and our nervous system. We have the natural ability to alter brain activity. And I've actually done functional MRI studies showing that when people bite down, it alters brain activity in a surprisingly significant way. So it's not just in your head. There's an actual physical change to activity in your brain in response to biting. So there's all this, and the future, I think, is wide open. We focused up till now on chemical pharmaceuticals. But I think we'll be moving ahead to electroceuticals or magnetoceuticals. And it's just the beginning. It's just the start of something that's going to, I think, take us generations to perfect. But in the end, we'll have a much better form of medicine. We'll have safer ways to alter brain function, to improve our performance, to improve our behavior. All sorts of benefits are coming. It's just a matter of finding the resources to do the development, even though the end result will be a cheaper form of medicine or a less expensive way than Starbucks to get us going in the morning. And all the work we've done, billions of dollars have been spent on learning how the brain works, how the healthy brain works, and how it goes wrong in illnesses. That information is out there, but it just sits there. I think that neuroimaging combined with neurostimulation will be unstoppable. And I'm organizing a scientific meeting. We had the last one in Honolulu, Hawaii last summer, and this summer it will be in Geneva, Switzerland, called Brainstem, to take this information and get both people interested in stimulation and people interested in neuroimaging in the same room together and start them talking and see what happens.
Fantastic. Which month is that taking place in?
It's mid-June in Geneva, Switzerland, before the Organization for Human Brain Mapping meeting, which is a large neuroimaging meeting. So my hope is to get neuroimagers more interested in neurostimulation. They're really experts about the brain, and I think they already know how to cure or at least reduce the symptoms of a lot of illnesses. And they don't realize it yet. They're walking around with this information stuck in their heads, unused. And if I can just get them to think about new ways to use it, I bet that there's going to be a lot of advances very quickly.
Smart Drug Smarts.
So thank you so very, very much to Professor Clark for taking the time for that conversation. I love it when an episode yields a new word for me, and that one we got both electroceuticals and magnetoceuticals, which I had never heard before, but are both very cool concepts to think about and look forward to. I find myself wanting to know more about this connection between our jaw and mouth and our central nervous system. That is so interesting and counterintuitive. I'm going to try to put the wheels in motion to get an episode in place about that concept, but mostly just really exciting to get to talk with somebody that so clearly is just charged up. When he was talking about the problems with the American medical system and the insurance industry and drug design, I mean, you could hear he was mad. And when he was talking about these next generation technologies, he was equally excited and optimistic. And I just love knowing that really, vigorous, excited people like that are working in these fields. I think we want more of that. But thanks again to Dr. Clark, and on to the Ruthless Listener Retention Gimmick.
Smart Drug Smarts. Ruthless Listener Retention Gimmick.
So I came home to Oregon for Thanksgiving this year. In Oregon, for the first time this year, this is a year that the laws changed, and it's now one of the increasing number of states that allows medical marijuana. So there's all these new medical marijuana dispensaries that are cropping up. You see them when you're driving down the roads here. Kind of a new thing. I'm not a pot person myself, but I've certainly been around it enough to know the propensity for marijuana to induce the munchies. The well-known fact that pot tends to make people want to eat and want to keep eating even after they should pretty reasonably be full. It has not been exactly clear to this point what's going on that causes that sensation, but neuroscientists at the Yale School of Medicine may have gotten closer to kind of figuring out the puzzle. There's a cluster of neurons in the hypothalamus called the POMC neurons, and in a normally functioning brain, the POMC neurons send out a chemical signal to tell the brain that, hey, I'm full, I'm done eating, you can stop. When they've done mouse studies to shut down the POMC neurons in mice, the mice get incredibly fat. And so researchers figured that the cannabinoids, the compounds in marijuana, might be doing something similar, sort of shutting down the POMC neurons temporarily and making people feel like eating. According to Thomas Horvath, one of the neuroscientists involved in this study, we found exactly the opposite. Instead, what happened was that the drug shut down neurons adjacent to the POMC neurons that normally actually tell the POMC neurons to slow down their activity. So the POMC neurons, in this case, their activity leapt up. But what they actually did switched completely. Instead of sending out a chemical signal telling the brain, hey, I'm full, the POMC neurons began making endorphins, which actually increases appetite, says Horvath. Even if you just had dinner and you smoked the pot, all of a sudden these neurons that told you to stop eating become the drivers of hunger. And finding a neuron that does a biochemical backflip like this and actually switches entirely the type of chemical signal that it's sending out is also a fairly new thing. The caveat in this study is that the study was done on mouse brains, not on human brains. But according to Horvath, because the hypothalamus is such an ancient part of the brain which has been around even before mammals, he, and I quote, would bet his life that the way that these neuron circuits work in mice is the same as they work in humans. You don't oftentimes find a research scientist saying that they'd bet their life on anything, so in scientific parlance, them's fightin' words. This effect, though it is a strong one, does not seem to be the only thing that's going on with the mystery of munchies. There's also research finding that cannabinoids light up the brain's olfactory center, which does smelling and makes people, mice, etc. more sensitive to smells. And still other studies have found that cannabinoids increase levels of dopamine in the brain. Dopamine, as we've talked about before, can increase feelings of motivation. And so if you're having something like your sense of smell triggered and your sense of motivation triggered at the same time, the smell of that food in the next room might become a pretty compelling argument.
Smart Drug Smarts, where we turn information into sound, into bits, into packet data that turns back into bits and sound and then into neurotransmitters that release funds that release mail-order synthetic chemicals that cross the blood-brain barrier to release augmented performance from your brain.
Okay, you heard it. That is the entire episode number 104 coming in for a landing. If you are in America or even an American elsewhere, hope you had a very, very happy Thanksgiving. Happy oncoming holiday season to everybody out there, wherever you may be. If you enjoyed this or other episodes, please pass the word about Smart Drug Smarts on to your friends and colleagues. And rest assured that the show notes for this episode will be online at smartdrugsmarts.com/104, including the links to everything that we talked about here. We've got a bunch of interesting stuff coming up in coming weeks, everything from brain fungus to oxyracetam to neurofeedback and more, so a lot of different things coming up in the near future. It should be a pretty exciting end of the year. As for me, I will be back at you next week, same time, same podcast, and with the same unflagging commitment to helping you fine-tune the performance of your own brain. Have yourselves a great week and stay smart.
You've been listening to the Smart Drug Smarts podcast. Visit us online at www.smartdrugsmarts.com and subscribe to our mailing list to keep your neurons buzzing with the latest in brain optimization. Smart Drug Smarts should be listened to for entertainment purposes only, although some guests on the show are medical doctors, most are not, and the host is just some random guy. Nothing you hear on this podcast or read at smartdrugsmarts.com should be considered medical advice. Consult your doctor and use some damn common sense before doing anything you think might have a lasting impact on your brain.